This lesson is about ratios, proportions, and variation. Using a calculator will help you solve many of the problems in this lesson. You may also want to keep paper and pencil handy to take notes. And remember, the problems you see on the screen are also presented in your study guide. In this lesson, we'll use ratios and proportions to solve problems. We'll also learn how to write formulas that'll give us a shortcut in solving certain types of proportion problems. But first, let's review the basics. A ratio is simply a direct comparison between two numbers. For example, to measure speed, we compare the number of miles traveled to the number of hours it takes to travel those miles. The ratio is miles to hours. If you travel 30 miles in 1 hour, the ratio is 30/1. Of course, when we have a 1 in the denominator, we usually just write the ratio as a whole number, 30 miles per hour. In addition to writing ratios as fractions and whole numbers, we can also write ratios as decimals. In baseball, the batting average is a ratio that's usually written as a decimal. We compare the number of a player's hits to the number of times at bat. The ratio is hits to times at bat. Suppose one player gets 6 hits in 27 times at bat. Divide 6 by 27. A player who gets 6 hits in 27 at-bats has a batting average of .222. In business, ratios are used in a variety of ways. The inventory ratio gives the ratio of total sales per year to the average value of the inventory. Suppose a store averages $875,000 in sales each year. Its average merchandise inventory is worth $225,000. What is the inventory ratio? Divide sales by inventory. Written as a decimal, the ratio is approximately 3.89. The ratio tells the store how many times the inventory turns over each year. The store will have to restock almost 4 times a year. Here's another way to use ratios. Suppose 1 bag of grass seed covers 5,000 square feet of lawn. 3 bags will cover 15,000 square feet. Here's the ratio of bags of seed to the amount of lawn covered. Now let's write 2 ratios. 1 bag covers 5,000 square feet. 3 bags cover 15,000 square feet. There are 2 equal ratios here. This is called a proportion. 1/5,000 is equal to 3/15,000. Now let's solve a problem using a proportion. 1 bag of seed covers 5,000 square feet of lawn. How many bags will you need to cover 32,000 square feet? X is the number of bags needed to cover 32,000 square feet. 1/5,000 equals X over 32,000. To solve for X, cross-multiply. 5,000 times X is 5,000X. 1 times 32,000 is 32,000. 5,000X equals 32,000. To solve the equation, divide both sides by 5,000. X equals 6.4. You can't buy 6.4 bags. You can only buy a whole bag, so you'll have to get 7 bags and have some seed left over. Here's another problem we can solve with a proportion. A weed trimmer with a 2-cycle engine runs on a mixture of gasoline and oil. The instructions say to mix 1 part of oil to 40 parts gas. A container is filled with 1 gallon of gas. How many ounces of oil should be added to the container to make the proper mix of fuel for the weed trimmer? We can solve this problem with a proportion, but be careful here. The problem tells us gasoline is measured in gallons. Oil is measured in ounces. That's because gasoline is usually purchased by the gallon. The oil used in two-cycle engines is sold in small containers and is measured in ounces. To solve the problem, we'll have to make sure we measure gas and oil in the same units. So, we'll convert gallons to ounces. There are 128 ounces in 1 gallon, so we have 128 ounces of gas. Now let's think about the oil-to-gas mixture we want. We'll write a proportion. The fuel is supposed to be 1 part oil for every 40 parts of gas. The oil-to-gas ratio is 1/40. We have 128 ounces of gas. We'll add X ounces of oil. 1/40 is equal to X over 128. To solve for X, cross-multiply. 40X equals 128. Divide both sides of the equation by 40. X is 3.2. 3.2 ounces of oil should be added to the gas. That'll provide the right mixture for the weed trimmer. Next, let's see how we can take some shortcuts in solving proportion problems. Suppose you're looking at the scale drawing of a building. 2 feet of real length in the building is represented by 1/2 inch on the drawing. To look at the sizes of things in the building, we'll use the ratio of the building's real size measured in feet to the drawing scale size measured in inches. On this drawing, the ratio is 2/0.5. What is the real length of a wall that is 1¼ inches long on the drawing? 1.25 is the scale length in inches. X is the real length in feet. Now we have a proportion we can solve. To solve for X, cross-multiply. 0.5 times X equals 0.5X. 2 times 1.25 equals 2.5. Divide both sides of the equation by 0.5. X equals 5. The wall is 5 feet long. If we want to know the real length of a different wall on the drawing, we'd change the right side of the proportion. We'd have a different value for the scale measurement, but we'd still solve for X. What if we wanted to know the real lengths of all the walls in the building? We could write several proportions. The left side of each proportion remains the same. Only the scale measurement on the right side changes. These proportions aren't difficult to solve, but if we approach the problem this way, we'll be solving a lot of proportions. Fortunately, there's a shortcut. We can write a formula to determine the real length of any wall in the building. We'll let R stand for real length. S will stand for scale length. To get the real length, R, we'll need to multiply the scale length, S, by some number that will both convert inches to feet and tell us how much larger the real size is. We'll call that number K. The general formula for converting scale length to real length is R equals K times S. Once we find K, we can use the formula to convert any scale measurement on the drawing. We know that R is 2 feet when S is 1/2 inch. We'll use these numbers to find K. In the formula, we'll substitute 2 for R and 0.5 for S. 2 equals K times 0.5. Now we can solve for K. Divide both sides of the equation by 0.5. K is 4. 4 is the multiplier that describes how the real size compares with the scale size. Substituting 4 for K in the formula gives us a specific formula for finding the length of any wall without writing a proportion. Suppose a wall on the scale drawing is 2 inches long. S equals 2. You want to find the real length of the wall. In the specific formula, substitute 2 for S. Multiply by 4. R equals 8. The wall is 8 feet long. We can also use the formula to determine the scale measurement from the real size. Suppose we want to add a square room that measures 16 feet on each side. R equals 16. What would be the scale measurement? Substitute 16 for R. Then divide by 4. S equals 4. The scale drawing would be 4 by 4 inches. Writing formulas makes the job easier and quicker than solving a new proportion problem every time. This process of writing a formula is so common and so important that we have a special vocabulary to describe it. We say that the real size, R, is directly proportional to the scale size s. We can also say that the real size varies directly as the scale size. We call the number k the constant of variation. The words varies directly or directly proportional tell us that one quantity in the formula is equal to k times some other quantity. M is directly proportional to t means the same thing as m equals k times t. C varies directly as the square of d means the same thing as c equals k times d squared. Problems like this are called variation problems. When we solve variation problems, we always work with two formulas and two sets of information. First, we write a general formula from the variation statement. In this case, real size varies directly with scale size, so we can write r equals k times s. This general formula can be used for any scale drawing. Next, we use the complete set of information. R equals 2 when s equals 1/2. We use this information to find the value of k. Substitute 2 for r and 0.5 for s. Now solve the equation for k. K equals 4. Now we can write a specific formula that indicates the value of k. R equals 4 times s. We can use this formula to answer any questions about a drawing that has this scale. A question usually appears as an incomplete set of information. What is the real size when the scale size is 2 inches? To answer the question, substitute 2 for s in the specific formula. Then solve for r. Instead of writing many proportions, we can use one general formula to solve many specific problems. We can use the same general formula for a different drawing, but if the scale is different, we'll have a different constant of variation in the specific formula. Let's look at a simple example and review the steps. X varies directly as the square of y. What is x when y is 3, if x is 27, when y is 6? The words varies directly tell us that this is a variation problem. X varies directly as y squared is the same as x equals k times y squared. We'll use this general formula to find the value of k. To find the value of k, we'll work with the complete set of information. Substitute 27 for x and 6 for y. Now we can solve for k. Square 6. Divide both sides of the equation by 36. K is 0.75. Once we know the value of k, we can write a specific formula. X equals 0.75 times y squared. Now we can solve the problem. We want to find the value of x when y is 3. Substitute 3 for y. 3 squared is 9. Multiply 9 by 0.75. X is 6.75. Direct variation has many practical applications. Here's an example. A person's threshold weight is the maximum weight a person can reach before his or her chances of dying prematurely increase significantly. If you weigh too much for your height, you're more likely to die at a younger age. For a man between the ages of 45 and 65, threshold weight varies directly with the cube of his height. Let T stand for threshold weight. H stands for height. The words varies directly with mean equals k times. The general formula is T equals k times h cubed. A middle-aged man who is 6 feet tall has a threshold weight of 201 pounds. We'll find the value of k by using this information. To solve for k, we'll substitute what we know about one threshold weight. A 6-foot man has a threshold weight of 201 pounds. Substitute 6 for h and 201 for t. 6 cubed is 216. 201 divided by 216 is approximately 0.93. Now substitute 0.93 for k in the general formula. The specific formula is threshold weight equals 0.93 times height cubed. By the way, this specific constant of variation is used to describe the threshold weight for middle-aged men only. We can't use it for young men or for women. We'd need a different constant. So let's use the formula to see how some middle-aged men fare with their height, actual weight, and threshold weight. Bob is 6 feet 6 inches and weighs 275 pounds. Dale is 5 feet 10 inches and weighs 180 pounds. John is 5 feet 5 inches and weighs 150 pounds. Before you start, be careful with the units here. We used feet to find the value of k, so we'll have to convert each man's height to feet. We'll round off decimals to the nearest tenth. For Bob, 6 feet 6 inches is 6.5 feet. Dale's 5 feet 10 inches is about 5.8 feet. John's 5 feet 5 inches is about 5.4 feet. We want to find the threshold weight for each of these men and compare it with their actual weight. So we'll substitute each height in the specific formula and solve for t. If someone weighs less than the threshold weight, he's probably in pretty good shape. If he weighs more than the threshold weight, he probably should do something about it. Let's see how Bob weighs in. Bob is 6.5 feet tall. Substitute 6.5 for h in the formula. Now find the cube of 6.5. Then multiply by 0.93. Bob should weigh no more than 255 pounds. He's 20 pounds overweight. This increases his chance of premature death. Let's see if Dale needs to lose any weight. His height is 5.8 feet. In the formula, substitute 5.8 for h. Then cube 5.8. Multiply the terms on the right. The threshold weight for a man Dale's height is about 181 pounds. Dale weighs 180. That's an acceptable weight. Now let's check John's weight. We'll substitute his height, 5.4, for h. Find the cube of 5.4. Now multiply the terms on the right. The threshold weight for someone of this height is about 146 pounds. John weighs 150 pounds. He's 4 pounds overweight. We've seen that in direct variation, one value varies directly with one other value. But we can also have variation problems where one value varies jointly with two or more values. X varies jointly with the square of y and the cube of z. That's the same as x equals k times y squared, z cubed. Notice we only have one k. That's because the constant of variation applies to all of the variables on the right side of the equal sign. We use the words varies jointly to indicate that the constant of variation is multiplied by two values. This is called joint variation. It's just another type of direct variation. Joint variation is common in a number of applications. For example, the volume of a solid varies jointly with the area of its base and its height. This is the area of the base of a cylinder. This is its height. To find its volume, we'd use the general formula V equals K times A times H. Another example of joint variation is interest on a loan. Interest paid, I, varies jointly with the interest rate, R, and principal borrowed, P. In this case, the constant of variation is the same as the length of time money is lent. Now let's look at a different type of variation. Suppose your favorite fast food restaurant doubles the price of French fries. Just yesterday you paid $1.50 for fries. Today the restaurant is charging $3 for the same thing. How do you suppose this will affect sales of French fries? In general, as the price of an item increases, its sales decrease. This is an example of inverse variation. Price varies inversely with sales. We can also say that price and sales are inversely proportional. The way we solve inverse variation problems is similar to the way we solve direct variation problems. With direct variation, we say x varies directly with y. X equals k times y. With inverse variation, we say x varies inversely with y. X equals k divided by y. We're dividing instead of multiplying, but we still have one constant of variation. In general, we'll write k in the numerator. Now let's solve a problem where x varies inversely with y. X is 8 when Y is 135. What is X when Y is 75? The general formula is X equals K over Y. To find the value of K, we'll work with what we know. Substitute 8 for X and 135 for Y. Solve the equation for K. Multiply both sides of the equation by 135. K is 1080. Now substitute 1080 for K. The specific formula is X equals 1080 over Y. Now we can use this formula to find X when Y is 75. Substitute 75 for Y. Divide. X is 14.4. Now let's look at a practical problem. The relative speed or velocity of connected pulleys varies inversely with the diameter of each pulley. Here we have a large and a small pulley. Notice how much more quickly the small pulley goes around as the rope is pulled. It has a very high number of RPMs. That's revolutions per minute. The larger pulley goes around more slowly. It has a smaller number of revolutions per minute. The larger the pulley, the smaller its velocity. Now here's the problem. A 15-inch diameter pulley is connected to a pulley with a 10-inch diameter. If the 15-inch pulley has a velocity or speed of 30 RPMs, what is the speed of the 10-inch pulley connected to it? We know that velocity, v, varies inversely with diameter, d. Let's see if we can write a formula that expresses this relationship. V equals K over d. Notice again that the constant of variation is in the numerator. To find the value of K, we'll use this information. Substitute 30 for V and 15 for D. To solve the equation, multiply both sides by 15. K is 450. Substitute the value of K in the general formula. The specific formula is V equals 450 over D. Now we can find the velocity of the 10-inch pulley. In the formula, substitute 10 for D. Divide. The velocity of the 10-inch pulley is 45 RPMs. That's 15 RPMs faster than the larger pulley. Now let's combine the different types of variation we've learned, direct, joint, and inverse variation, in one problem. D varies jointly with E and the square of F, and it varies inversely with the cube of A. D equals 3.375 when E is 2, F is 6, and A is 4. What is D when E is 5, F is 8, and A is 2? That's a lot of information, but the problem won't be difficult to solve if we take it one step at a time. First, we'll write a general formula. Since we have inverse variation, we know the formula will have a denominator. Everything with which D varies inversely goes in the denominator. That's A cubed. Everything with which D varies jointly goes in the numerator. That's E times F squared. What about K? The constant of variation goes in the numerator. This is the general formula. Use the information we have to find the value of K. Substitute 3.375 for D, 2 for E, 6 for F, and 4 for A. Now simplify. 6 squared is 36. 36 times 2 is 72. 4 cubed is 64. Multiply both sides of the equation by 64. Divide by 72. K is 3. Now we can write the specific formula. D equals 3E F squared over A cubed. We want to find D when E is 5, F is 8, and A is 2. Substitute these values in the formula. Simplify. 8 squared is 64. 2 cubed is 8. Cancel. Multiply. D is 120. Here's a practical example of combined variation. The amount of weight a shelf can hold varies with its three dimensions: the length, the width, and the thickness of the board. A wider shelf can hold more weight than a narrow one. A thicker shelf can hold more weight than a thin shelf. This means the amount of weight varies directly with width and thickness. A longer shelf will hold less weight than a shorter shelf that has the same width and thickness. The amount of weight supported varies inversely with the shelf's length. If the shelf is too long, it might sag or break. In general, the load a board can support varies jointly with the width of the board and the square of the board's thickness, and varies inversely with the length of the board. Let's write a formula that describes the relationship between the load a board can hold and its width, length, and thickness. We'll let X stand for load. The load a board can support is equal to the constant of variation times the width times the thickness squared, all over the length. Notice the numerator contains the constant of variation in everything with which the load varies directly. The length is in the denominator because it varies inversely with the load. We can use this general formula for any load-bearing board that has supports at each end. We can write specific formulas for boards made of different materials. Suppose a beam that is 4 inches wide, 2 inches thick, and 3 feet long supports 1,000 pounds. How much weight could a beam with the same width and thickness support if we increased its length to 6 feet? To find out, we'll have to determine the constant of variation. To find K, first substitute the values we know in the formula. X is 1,000, width is 4, thickness is 2. Length is 3 feet. Be careful here. We've used inches for all the other units, so we'll use inches here also. 3 feet is 36 inches. L is 36. Now let's solve for K. First, simplify the numerator. 2 squared is 4. 4 times 4 is 16. Next, multiply both sides of the equation by 36. Then divide by 16. K is 2,250. Now we can write a specific formula for determining how much weight any beam made out of this material can hold. In the general formula, substitute 2,250 for K. We want to find the load capacity of a beam with these dimensions. Again, we're working in inches, so for the 6-foot length we'll use 72 inches. Now we can substitute these values in the formula. Substitute 4 for W, 2 for T, and 72 for L. Now simplify. 2 squared is 4. 4 times 4 times 2,250 is 36,000. 36,000 divided by 72 is 500. The beam can only support a load of 500 pounds. That's half the weight the shorter beam was able to support. That makes sense. A beam twice as long will only support half as much weight. Let's work with a shorter beam to see if we can get it to hold even more weight. We'll flip it on its side like this. Now the width is 2 inches. The thickness is 4 inches. Length is 36 inches. This is the same beam we used before, so we can use the same specific formula. We've just positioned it so the width is 2 and the thickness is 4. The length is still 36. We want to find the load capacity. Substitute width, thickness, and length in the formula. Now simplify the numerator. 4 squared is 16. 2,250 times 2 times 16 is 72,000. 72,000 divided by 36 is 2,000. Flipped on its side, the beam can hold 2,000 pounds. We can double the weight capacity just by putting the beam in a different position. A beam made from a different material will have a different weight capacity. But we can still use this general formula. The only thing different will be the value of K. A different material will have a different constant of variation, but the general formula remains the same. Use it, and next time you buy or build a bookcase, you can avoid shelves that sag. In this lesson, we worked with proportion and variation. If you had any trouble with the ideas in this lesson, work through it again or ask someone to help you. Otherwise, you're ready for the examples and problems in your study guide.